morning everyone. Here Ritu Singh from LIT Saregam. Today we are one chapter, that is diversion headwork, and we will continue through design aspects. In the earlier lecture we have gone through failure due to surface and subsurface flow. Okay, so in the design aspects for the subsurface flow and the surface flow. So, what is subsurface flow? How can we design when the failure due to subsurface flow? So, it can be designed like subsurface flow. We have piping failure, and it does. What should have it done that the piping failure should not occur? So, your downstream pile, whatever downstream pile you are providing, must be provided to reduce the exit gradient and prevent piping. For example, you are having a weir over this area, and this is your upstream side, and this is your downstream side. So, what this design is saying that if you provide sheet piles over this area, then your piping failure may be reduced, because your water, the seepage water, it takes time to travel this area, and it will not create your piping type like hollow pipes under the foundation. So, first of all we have to provide the downstream pile. Okay. Second is impervious floor of adequate length, means whatever the floor we are providing, it should be of impervious. Before we are having pervious floor. So, if it is impervious, the seepage will be less or negligible. So, we can have provide the increase of path of percolation and reduce this hydraulic gradient. So, whatever the hydraulic gradient means one angle it is formed, like this is water structure. So, this is hydraulic gradient. One angle is formed to travel the water from upstream to downstream. So, this hydraulic gradient, this reduce the hydraulic gradient, and the seepage forces of the water is reduced. Okay. Now, seepage path is also increased by providing piles and impervious floor to reduce the uplift pressure. So, whatever the subsurface failure due to uplift pressure also. So, if we provide the impervious floor and downstream pile, then both this failure can be eliminated. The thickness of the floor should be sufficient to resist the uplift pressure due to subsurface flow. So, if there is a your uplift pressure, so it also can be reduced by providing the this sufficient impervious floor. Then the suitable graded inverted filters of this suitable graded yes. So, the seepage path is increased by providing piles and impervious floor to reduce the uplift pressure. So, if there is a uplift pressure, if we this failure due to uplift pressure, then if we have impervious floor of sufficient thickness, we can reduce the uplift pressure, and this through the piles we can reduce the piping failure. So, the thickness of the floor should be sufficient to resist the uplift pressure due to subsurface flow. Now, suitably graded inverted filter should be provided at the downstream end of the impervious floor to check the migration of soil particles along with water. So, the filter layer loaded with concrete blocks. So, this is your hydraulic structure, and this is water upstream, downstream. So, if there is a some inverted filter over this area, like drainage over this area, so whatever the seepage water you have, so it flows along with the soil. So, what is the role of this inverted filter? That it will prevent the soil to flow along with the water. So, your failure will be eliminated, your failure will be neglected. So, this should be provided at the downstream end. Okay. Now, second is this surface flow, the failure due to surface flow. So, what we can do to eliminate the failure due to surface flow? So, the piles or cut-off wall at the upstream and downstream end of the impervious flow should be provided up to the maximum score level to protect the main structure against score. So, same here. So, we have to provide the cut-off wall at the upstream. This is upstream end and this is downstream end. So, we have to provide the cut-off wall over the at the upstream and downstream end of the impervious flow. So, this flow should be impervious to the maximum score level, means up to which the seepage water is travelling. So, at the maximum score level we have to provide this cut-off wall to eliminate the surface flow. Okay. The launching apron should be provided at the upstream and downstream end to cover the main structure against screw. So, here we should also provide a launching apron. Your thickness should be as high, and in the downstream end also we have to provide the launching apron to eliminate the surface flow and to have less score due to this hydraulic jump. So, devices require the downstream to dissipate energy. So, some device we have to put in the downstream side to dissipate the energy due to flow due to hydraulic jump. So, for the large drops like hydraulic jumps is used to dissipate the energy. Okay. Additional thickness of the impervious floor. Again problem हुआ, क्या हो रहा है? कनेक्ट नहीं हो रहा बराबर, हिल जाता कुछ ऊपर में परमानेंट अभी वो चालू है अभी. So, edit करना पड़ेगा सर. Okay. This additional thickness of the impervious floor is provided at the point where hydraulic jump is formed to counterbalance the suction pressure. Okay. So, we have to provide the additional thickness to the downstream end to eliminate this point to, and this due to hydraulic jump whatever suction pressure is created we can eliminate by providing additional thickness of this impervious floor. And the floor is constructed at a monolithic structure to develop bending resistance or beam action to resist the suction pressure. Okay. Now, we have two scientists over here to explain this design aspects, that is Khosla theory. Before that we have Blake theory, but it failed due to some reason, and Khosla have came over, and we are designing this canal or hydraulic structure according to the Khosla theory. So, this many important hydraulic structures such as weir, barrage were designed on this basis of first of all we have designed on the basis of Blake theory between 1910 to 1925. But in 1926-27, one upper channel canal, this upper channel canal siphons were designed on this theory, Blake theory, and it have this problem of undermining trouble. So, various investigation have started, and ultimately we are started to follow the Khosla theory. So, we should know about the main points of the Khosla theory, that is what Khosla have designed to the hydraulic structure. So, what you have designed that your outer faces of the end sheet piles were much more effective than the inner ones and the horizontal length of the floor. So, what they have designed that, for example, this is your impervious flow, and upstream, downstream. Okay. So, what he is saying that your outer faces of the sheet piles. So, this outer faces of the sheet pile is much more effective than the intermediate pile, and the horizontal length of the floor. So, whatever the horizontal length of the floor he is travelling, your outer faces is much more effective, and intermediate piles of smaller length were ineffective except for local redistribution of the pressure. So, intermediate piles, if we are providing intermediate piles of smaller length, it is he have considered that it is ineffective. Okay. Undermining of flow started from the tail end. Tail end means your the water is getting traveling through this, your seepage water getting traveling through this area, and your undermining process start at this area where the pressure exists. So it was absolutely essential to have reasonably deep vertical cutoff at the downstream end to prevent undermining. So what he is saying that your undermining of flow started at the tail end. So what you have to do? You have to provide this deep vertical cutoff at the downstream end. So your water get traveled through this area, and we can eliminate this undermining failure. Now Khosla and associate took over the account of flow pattern below the impermeable base of the hydraulic structure to calculate uplift pressure and exit gradient. So he also calculated the this uplift pressure and this exit gradient. Okay, what is exit gradient? The gradient provided at the exit, that is at downstream end, whatever the gradient is there. So seeping water below the hydraulic structure does not follow the bottom profile of the impervious flow as stated by Blake, but each particle traces a path along a series of streamlines. So what Blake have told that your water is getting travel through a horizontal layer, like one sheet piles you have considered, and your water is getting travel through this B length or L length. So you have counteracted this point, and he have come through that that your each particles of water traces its path along a series of streamlines. So this Khosla have given some independent variables. So method of independent variable is most design do not come from elementary profile specific cases, and in actual cases we may have number of piles at upstream level and downstream level and intermediate points, and the floor also have some thickness. So we have number of piles at upstream and downstream and intermediate points, and your flow should also have some thickness. So Khosla solved the actual problem by empirical method. Some empirical method he has given, known as method of independent variables. So he has solved this problem with the help of this empirical, and he has given the name as independent variables. So this method consists of breaking a complex profile into a number of simple profiles, each of which independent amenable to mathematical treatment. So he has given us some mathematical solution also in terms of pi and alpha. So this apply correction to the thickness of the slope of the floor. An example of complex profile shown in the figure is broken up as following simple profiles, and pressure as key point is obtained. So we will have we'll go through this Khosla theory and a very empirical method we will understand in details. So this this four conditions have given this Khosla, that your straight floor of negligible thickness with pile at upstream end. Means first condition, if I show you the figure over here, so he has given your upstream pile. First condition is your upstream pile, second condition is your sheet piles at downstream end, and third condition is straight flow of negligible thickness with pile at intermediate points, and the fourth is the pressure is obtained at the key points by considering the simple profiles. So for determining the seepage below the foundation of this hydraulic structure developed by independent variables, so in this methods we have actual profiles of the weir, which is complex, divided in number of simple profiles, and each of which can be solved by mathematical without difficulty. So the most useful profile considered is, first is the straight horizontal flow of negligible thickness provided sheet piles at the upstream end and the downstream end, and the second is the straight horizontal flow depressed below the bed without any vertical cutoff. So this 2 points we have considered, like upstream piles and downstream piles, and this with a floor thickness without any piles. Thank you. Here I will proceed with the intermediate points and other factors in the next lecture. Thank you.